Most students draw free body diagrams, but very few understand why they draw them. They follow steps, they copy examples, and still, they don't really understand what they are doing. A free body diagram is not a drawing technique. It's a way of thinking. It's how we make the invisible visible. A free body diagram, or FBD, is the simplest way to reveal the forces and moments acting on an object. The goal of an FBD is to reveal the forces and moments we want to determine. You take a real element, a beam, a column, or even yourself, and you mentally detach it from everything touching it. That isolated element is the free body. Everything you removed is the surroundings. And now something important happens. The surroundings don't disappear. They come back as forces and moments. Most of these forces come from contact, supports, connections, surfaces. But we should also remember that the Earth is part of the surroundings. Through gravity, it applies a force on the body, its weight. And unless this force is negligible compared to others, it must be included in the diagram. Now we draw. Every interaction becomes a force or a moment. Just arrows. No decoration. No architectural ego. This is the one place where minimalism is not a style. It's mandatory. Place each arrow at the point of interaction, in the correct direction. And that's it. You are not limited to a single element. Depending on what you want to find, you can choose different free bodies. For example, you sitting on a chair. You can draw a free body of yourself, a free body of you and the chair together, or even a free body of a single leg of the chair. In each case, the forces are different. But in all cases, we draw only the external forces. Let's use this idea. First, take only the person. The chair pushes up. The floor pushes up also. Weight pulls down. Now expand the system. Take the person and the chair together. Now the force between them disappears. And we are left with the weight of the person plus the weight of the chair downward and the floor reaction upward. Now isolate just the leg of the chair. The forces acting on it are its own weight, the force from the floor, and the forces from the rest of the chair. Why do we draw free body diagrams? Because structures never tell us their forces directly. A column doesn't say,
I'm carrying 12.7 kilonewtons.
To reveal the forces acting on an element, we must isolate it and let physics speak. Once the free body is defined and all forces are drawn, we move to the next step. We assemble equations. In statics, every free body is in equilibrium. So, the sum of forces equals 0, and the sum of moments equals 0. From these equations, we find the unknown forces. Now, let's use this on a real structure. Take a beam, 4 meters long, supported at both ends. A load of 2 kilonewtons acts downward 1 meter from the left support, point A. Our goal is to find the reactions. First, we draw the free body diagram. The beam is isolated. The supports become reactions, AY at the left and BY at the right. Support A could also provide a horizontal reaction, but since there are no horizontal forces, that reaction is 0. The load is a force of 2 kilonewtons downward. Now we write the equations. We start with moments. If you're unsure about moments and their direction, we cover that in separate lessons. Sum of moments about point A. The reaction at B creates a counterclockwise moment. The load creates a clockwise moment. So, by times 4 minus 2 times 1 equals 0. From this, by equals 0.5 kilonewtons. Now we use vertical equilibrium. Ay plus by minus 2 equals 0. So, Ay equals 1.5 kilonewtons, and we are done. The free body diagram gave us the equations, and the equations gave us the solution. Without the free body diagram, this would not be possible. This is the real skill in structural thinking. Solving equations is not the challenge. Choosing the right free body is. Because once the free body is right, the equations become almost trivial. Once you master this, you start seeing forces everywhere. In beams, in chairs, in people leaning on walls, which is useful, and occasionally socially inconvenient. But more importantly, it gives you clarity. And this is exactly what we develop throughout the course, Physics and Structures Made Simple for Architects. Not isolated steps, but clear principles and a reliable way to approach any problem in statics and strength of materials.